We're going to pick up where we left off in the last lecture, where we were working on this example where a cake has been removed from an oven, and it's measured at 300 degrees whenever it comes out. 3 minutes later, the temperature is 200 degrees, and we assume that the room temperature is 70 degrees. We want to know how long it takes to cool to 75 degrees. What we were able to do last time is solve the differential equation after we set up the model all the way down to here, where we have T is equal to 70 minus C e to the negative kt. What we don't know is what C is and what K is. So we're going to use, first of all, the initial condition right up here to solve for C. And then we're going to use the information provided in the problem here that at 3 minutes we know the temperature is 200 degrees. Those two pieces of information about the profile of the temperature is going to help us find those unknown constants that we have. So let's start by using the initial condition, which is T of 0 is equal to 300 degrees, and plug that into our model equation that we have now. And so we have 300 is equal to 70 minus C e to the 0, because we have negative k times 0, which is just 0. Of course, we know e to the 0 is equal to 1. So this gives us 300 is equal to 70 minus C. If I solve that for C, I end up with C is equal to negative 230. Now I'm going to take that negative 230 and plug it into my model equation right here, and so I end up with T of T is equal to 70 minus a minus 230, which will be plus 230, e to the negative kt. Now the question is, what is K? We'll find K using that other piece of information that we have, that is at T of 3, we know it's 200 degrees Fahrenheit. So simply plug that in. 200 would then equal to 70 plus 230 e to the negative 3k, because T is now 3. So let's subtract 70 from both sides and divide everything by 230. We end up with 130 over 230 is equal to the 70s cancel, so it's just e to the negative 3k when we've divided off the 230. Of course, we can cancel out 10 out of the top and bottom of the fraction on the left-hand side, and then take the natural log of both sides. That's going to give us that the natural log of 13 over 23 is equal to simply negative 3k, because natural log of e to the negative 3k cancels and leaves a negative 3k. Divide the negative 3 across, and k is then negative 1/3 of the natural log of 13/23, or approximately 0.19018. So if we plug that back into our model equation that we'd come up with up here, we have T of T is equal to 70 plus 230 e to the negative 0.19018. And now we have enough information to answer the question of how long it takes to cool to 75 degrees. We want to find what T, the little t, is, so that this whole thing is equal to 75 degrees. So to answer that question, how long to reach 75, we're going to set it equal to 75 and solve for little t, which is time. So 75 is equal to 70 plus 230 e to the negative 0.19018t. Subtract the 70 across, divide by 230. Basically, some algebra occurs here. SAOH is my abbreviation for that. You end up with the natural log of 5 over 230 divided by negative 0.19018, or approximately 20.1 minutes. Voila! We can answer that question. All right, so what we've done in this process here is we've gone from finding the constants, C and K, to now being able to have a full model, to now being able to have the solution to our first question. What about the second question? How long does it take to reach room temperature? Does anybody see a problem with that?
It's going to equal 0.
Okay, so it's going to equal 0, because when you subtract 70 from 70, like if you set the left-hand side right here equal to 70 and you move the 70 across, it equals 0. Now what was the next step after that? Divide. Okay, so 0 divided by something still 0. Then what? Natural log. And then alarms go off, right? You can't do that. You can't take the natural log of 0. There is no natural log of 0, because nothing to a power will ever equal 0. So what's the answer? When will it reach room temperature?
According to this model, it doesn't.
According to this model, it doesn't. And in fact, why not? I mean, look at the picture of a graph of something that's cooling. If this is 70 degrees, okay, by the way, 70 is also a critical point in this, which means if it started at 70, it stays at 70. And we know something about autonomous equations, ones without little t's on the right-hand side, that have critical points. All temperature profiles are going to do this, right? They asymptotically approach it, but never actually reach it. Okay? Now, in the real world, would we say it actually reaches 70 degrees? Well, within some, margin or measurable error, we would never be able to measure something exactly anyway. So our devices that we use to measure temperature would be accurate to within maybe plus or minus 0.1 degree or plus or minus 0.01 degrees, depending on how accurate of technology we could use to do that. At some point, it will get within any interval that we want around it, and we can say, well, it's close enough. Okay? So, Gerald, I think your answer is the best answer. Mathematically speaking, the model says never. Realistically, it's within some range of that room temperature at some point in time. So all I'm going to put right here is for this question is mathematically never. Never actually reaches room temperature. But then again, one of the assumptions that we've made all along is that the room temperature never changes. But even the room temperature in real life is fluctuating, isn't it? So if it goes up just a little bit, they'll intersect at some point anyway. So mathematically speaking, if we lived in a perfect mathematical world, it would never actually reach it. But that's not the case. All right. So that is our Newton's cooling model. Let's move on and look at the mixture problems, which we also have the ability now to solve because they are also separable or could be thought of as linear. In fact, I think this one I'm going to do the linear way to do this. So let's refresh our memories about how we set up the model for a mixture problem. We've got a large tank that contains 300 gallons of brine solution or salt solution. So the salt is entering and leaving the tank. The brine solution, another brine solution is being pumped in at a rate of 3 gallons per minute. We're going to assume that this is all mixed together. Okay, so it's thoroughly mixed at any given time t. Then the mixture is pumped out at the same rate that it's pumped in, so that the volume of this tank is not changing. And we're going to assume that the concentration of the salt entering is 2 pounds per gallon. And we're starting with 50 pounds of salt initially in the 300 gallons. The question is, how much salt is in the tank after a long time? So what I want to do is first solve the model. Actually, first I want to set up the model. Then I'm going to solve the differential equation and the initial value problem. Then I want to answer the question of what happens after a long time. Now, what do you think I mean when I say what happens after a long time? What mathematical function or process am I going to use for that? Approaching infinity. We're going to let the limit occur, right? We're going to take the limit as time goes to infinity and see what the behavior of the function a of t would be. So this right here, there goes my pen. And it's back. This right here means what's the limit? The limit as t goes to infinity of a of t. That's the question we really want to answer. What's the limit as t goes to infinity of a of t? But first, let's build our model. Now, how do we do mixing problems? What's the key concept for building a mixture problem model? Exactly. So dA dt is rate in minus rate out. So let's draw a picture. We know coming in I have 3 gallons per minute, and going out I have 3 gallons per minute. And what's the concentration coming in? Does it tell me? 2 pounds per gallon. So that would tell me how much salt is coming in every minute, right? It's 2 pounds per gallon, and 3 gallons per minute, so that's 6, right, pounds per minute coming in, which I'll just multiply those. We're going to let the amount in here at any time t be A, and what's the volume? 300. All right, so put these pieces together, see what we got. The rate in is the flow rate coming in, which is 3 gallons per minute times the amount or the concentration, which is 2 pounds per gallon. And the rate going out is 3 gallons per minute. I should be writing GAL since that might be confused as grams, but I'm going to be lazy. Not go correct all of that. It's gallons per minute, right? And what's the concentration leaving? How much is, what's the concentration of the amount going out? Because remember, all I'm doing is multiplying by the flow rate times the concentration. That gives me an amount of salt, right? Because the gallons cancel and I'll have pounds per minute. Right? So 6 pounds per minute is coming in. How much is leaving? What's the concentration of what's going out? A over what? 300. It depends on the amount of salt in there, right? We don't know how much salt is in there other than to say it's some variable A, right? So however much salt is in there, how many pounds of salt, that's A, divided by how many gallons are in there. That's going to be pounds per gallon. Make sense? So this is times A over 300. Which means my equation is dA dt equals 6 minus, and that was 3 times A over 300, which is going to be A over 100. And we also have an initial condition, so we can write this as an IVP. dA dt equals 6 minus A over 100, and A at 0 is, careful, A is just amount, not concentration. We're modeling amount. There's another model you could set up that's based on concentration, but it's more complicated to solve and set up, so we're using the easier one, which is modeling just the total amount of salt. So A is 50 at 0. So there's your initial value problem. By the way, you'll notice that is, in fact, separable, so I could solve it the same way I did the Newton's law of cooling, but it's also linear. I'm going to solve this differential equation as a linear differential equation. The only reason I'm doing that technique is to remind you, so you can say it one more time, how we solve linear ones. Now linear, remember, means all the y's and dy dt's, all the derivatives of y are to the first power, no two are multiplied together. Any coefficients they have may depend on the independent variable, but not the dependent variable a. In other words, I can write it like this. dA dt plus, and I'm going to move the a term over to the left-hand side. And I'm going to even write it like this, so I can see it as a coefficient. Since it's a over 100, that's 1/100th of a, equals, and leave the 6 on the other side. See how that now looks linear? Now what's the technique for solving linear differential equations? Our mu, or called our integrating factor. The mu is equal to E integral over 1 dt. I'm going to write that a little bit better so you can see that. Mu equals E to the integral of the coefficient, right, this here. Oh, I hate that highlighting tool. This right here. which we would call our P whenever we introduce this. That's 1 over 100 dt. Which means e to the t over 100. All right? Because the integral of 1 over 100 is t over 100, or 1/100 is t. But it's still e to that power. And then what do we do with the mu? You remember? Multiply it where? Multiply it here. If we multiply everything by mu, you end up with e to the t over, can't write very well, e to the t over 100 times dA dt plus 1 over 100 e to the t over 100 all times a equals 6e to the t over 100. And then, what can we do to the left-hand side? It's the product rule in reverse, right? That happens to be mu times a. E to the t over 100 times a equals 6e to the t over 100. Integrate. Boo. Yeah. All right, let me come back up here now. I end up with, on the left-hand side, since an integral of a derivative is just the integrand e to the t over 100 times a equals, and the integral of 6e to the t over 100. Not quite. If I do 6 over 100, e to the t over 100. Remember, when I take the derivative of that, I would have to multiply by the derivative of what's inside, which means multiply by 1 over 100. So really, I want the 1 over 100 to cancel with something and leave behind a 6. So 600. You're on the right track. You were just thinking in reverse. So 600 e to the t over 100 plus c. So what I'll do here is divide both sides by e to the t over 100, or multiply by e to the minus t over 100. So I end up with a equals 600 plus c e to the minus t over 100. That is a minus, if you can't see that. E and a minus t over 100. Beautiful. Now, technically, I can actually answer my question already, but I'm going to still finish the initial value problem for the sake of completion. How do we find the C? Okay, so use the initial condition, which is A of 0 equals 50. So 50 equals 600 plus C e to the 0. Agreed? So e to the 0 is just 1. So what is c? Negative 550. So a of t is equal to 600 minus 550 e to the negative t over 100. And now we can come back to the original question of what's the limit as t goes to infinity of 600 minus 550 e to the negative t over 100. So this part right here, the 600, obviously is not dependent on t, so it hangs around. What happens to e to the minus t over 100 as t gets large? It gets itty bitty. Why? Well, it's the bottom of a fraction, right? E to the minus t over 100 is the same thing as 1 over e to the t over 100. And as this exponential gets large here, or the exponent gets large, then e to a large power gets really big. In fact, it gets big fast, but it's the bottom of a fraction, so the whole fraction goes to 0. That's an important thing to remember, is that when you've got anything that is larger than 1, which e is, raised to something that's getting large negative, right? 2.7 or so, raised to something that's getting large but negative, that thing's going to go to 0. So I'll write that in here. This goes to 0. So what's the amount after a long time? Close to 600 pounds. Which makes sense, by the way, if you think about the problem. If you have a solution coming in that is 2 pounds per gallon, eventually what's going to be in the tank has a concentration of 2 pounds per gallon. Right? Eventually all the water inside the tank that was there originally is going to be replaced by something that matches the concentration of what was coming in. So it will stabilize at 2 pounds per gallon, matching what's coming into it. And if there are 300 gallons in there, at 2 pounds per gallon, that means you're going to end up with 2 times 300, or 600 pounds in there. Okay? All right, so that's all of 3.1, which is what I want to cover in terms of sample problems. Now, when we were looking at 3.1, we were limiting ourselves to talking about linear models. I'm going to introduce a couple of new cases, actually mainly one new case. In 3.2, a new type of model that we haven't considered before, at least not directly, and try to solve it. That's a nonlinear model. All right, so give me a second. Let me get out of this recording.